My name is Jenna Logsdon. I'm in the chemistry department here at Northwestern, where my research focuses on asking simple questions to solve a really big problem, which is the energy crisis, through a technology called organic photovoltaics. Now, we all know that the Earth is warming at an alarming rate. Right now, we're about 1 degree on average warmer than we have ever been. And if we continue to burn fossil fuels and emit greenhouse gases, we could be 10 degrees warmer within the next 100 years. And we're already starting to see the effects of this with all the natural disasters this year. This is actually a photo outside of my parents' house after Hurricane Irma in Florida, which really devastated so much of the Caribbean. And some of you may have been affected by the wildfires in California caused by the heat waves and droughts. So how are we going to solve this problem? Well, we need to start focusing on renewable energy resources, and our largest is the sun. If we cover certain portions of the Earth with the red dots here with solar panels, we can get all the energy we need. And that really only totals to about the size of Spain. So we really can just start focusing on using solar energy. Our main technology used today is silicon solar panels, and these work really great, but they're kind of limited to what you see in the photos here. You can have them on roofs and you can have them in fields, but they're just huge and black and bulky. And they also cost a lot of energy to make in the first place. You have to heat the silicon to thousands of degrees to purify it before you can make a solar cell. So the energy payback can be many, many years. That's why my research focuses on a different technology called organic photovoltaics. And organic meaning carbon-based, so they're really cheap. You can actually put these in a solution and print them onto plastic like you would ink onto paper. So then you could really just put it anywhere. You could put them on the sides of buildings. You could even have your own portable phone charger. And you can even wear it if you wanted to. But the problem right now is that we don't understand them well enough to really get the efficiencies that we would need to implement them into society. So how do we go about designing one of these organic photovoltaics? Well, if we're going to make a solar cell, it really needs to absorb sunlight. And we're really shooting for that large portion of the solar spectrum, the visible portion there. So it's going to be something colorful, something we can see. And if we want solar to be one of our main energy resources, we need it to be accessible to everyone. They need to be practical. So they're going to have to be cheap until everyone could buy one. They're going to need to be stable. These are going to be outside, subjected to the environment and oxygen. They're going to need to stay stable. And they also need to be easily manufactured. So one of the main molecules we're looking at right now is called perylene diamide. And it's red, so we know it absorbs a portion of the visible spectrum, but it's also been used in red car paint. So we already know it's stable and easy to manufacture. But most importantly, organic photovoltaics need to make electricity. So we do that by having two different molecules. The first likes to donate electrons. And electrons are negatively charged particles, so when it donates that electron, itself becomes positive, and it will give that to the second molecule, which then becomes negative. And by having this flow of charge, we can get electricity. And I'll show you a little bit more about how that works. So we have an organic photovoltaic device here. You have your two materials, your donor and acceptor material, mixed together. And first, it's going to absorb sunlight, and that's giving it extra energy and exciting it, creating these bound charges in something called an exciton. And we all learned a long time ago that opposites attract, so these charges just want to come back together and do absolutely nothing for us. But if this exciton can migrate to the interface between the donor and acceptor, it can then separate. And now these charges aren't attracted to each other anymore and become useful. So we can collect them, getting that flow of charges and making electricity. And I don't know about you guys, but that seemed pretty complicated to me. So that's where my research focuses on simplifying this whole design. So instead of just having the donor and acceptor materials just randomly mixed together, causing a lot of disorder, what if we can make something that's much more simplified and ordered? And where we have the donor and acceptor next to each other, and we know where they are, we know how big they are. And we can do that by attaching them together through chemical bonds, and then forcing them to stack in this way, which kind of emulates that idealized, simplified design. One way we've been able to do this is by adding incompatible side chains to each side of the donor and acceptor. So if we have one side that doesn't like water and one side that does, they're never going to want to come together, and they'll stack in this nice way shown here. With that ability, we'll be able to see in a simplified manner how the charges are moving. And we actually have shown that this is stacking in that way by just put this molecule on a glass slide and look at it under a microscope, and you can see that it's forming these beautiful long rods like we wanted it to. And so with this highly ordered, simplified structure, we can use this model system to understand how the charges are moving, and then apply this to devices, and definitely we're going to get better efficiencies, because organic photovoltaics are going to be a very useful technology for the future. Thank you.